It's a pleasure to introduce Martin Keenan, a very familiar figure to us. Martin has been a chapter member since 2003, and today is his 14th presentation to the chapter. His most recent presentation, the British B-bombers, was typical of the very comprehensive presentations that he provides. Martin is a lifelong second-generation aviation enthusiast who acquired an interest in historical aircraft after a family visit to the first Hamilton Air Show in 1975. He is a published aviation writer and photographer, and also a former secretary-treasurer of the chapter. Over to you, Martin, for another, but I'm sure will be a very excellent, comprehensive presentation.
All right, thanks, Gord. Is the audio good? You can hear me? Okay, good. All right. Okay. When I was a youngster back in the 70s, aircraft were a frequent topic of conversation among my contemporaries. And one of the aircraft that every boy my age seemed to have heard of was the XB-70 Valkyrie. It's understandable. It's a very exotic-looking aircraft. It looks mind-blowingly fast, and even 50 years later, it looks surprisingly modern. Part of the reason why everybody seemed to know something about this aircraft may be this article from September 1965 National Geographic about the United States Air Force. Issues of National Geographic were everywhere in this era, and several of my public school classrooms had this particular issue. And as the photo shows, the XB-70 featured prominently in the article. It also featured prominently in the large fold-out illustration in that issue on the 1964 era U.S. Air Force inventory. So I knew something about the XB-70. I knew that it was a limited research program. I knew that only 2 of these aircraft had ever been built. I had also seen film in a documentary that I saw at school for some reason of a very dramatic landing with flames coming out of the landing gear. And there were also some other vague rumors about this mythical beast. One I remember was that somebody saying that it had steel tires. So I was very interested in knowing more, but this is an era where this kind of information was kind of hard to come by in your average library. Then I learned from a casual conversation with a staff member at my high school that there was an aviation museum that I hadn't heard of in Ohio, and it had an XB-70 as an exhibit. So I got a chance to visit the museum in November 1981, and yes, that's me. That's what I looked like then, and see the XB-70 for myself. I also had an opportunity to purchase a book on the subject and finally learn the aircraft's actual story. It was one of the first serious aviation books I ever purchased, but as my wife will confirm, far from the last. What I learned from that book and from my many subsequent visits to the Air Force Museum in Dayton is the basis for the story I'm about to tell. The reality of military strategy in the post-World War era, post-Second World War era was the existence of nuclear weapons. And just as important as the weapons themselves was having the means to deliver them to a potential target. And at the time, the only way to do this over intercontinental ranges in a reasonable length of time was by aircraft. Now, the earliest American nuclear delivery system was the B-29, which had originally been developed for conventional bombing. In the post-war era, this was fairly quickly replaced in the strategic bombing role with the Convair B-36. The B-36 was originally developed before the American entry into the Second World War to provide the capability of attacking targets in Europe with nonstop missions from the United States. So this was a pretty impressive feat at a time when even one-way trips across the Atlantic were challenging. So doing this with 1941 technology resulted in a huge aircraft with tremendous range and endurance, but relatively low speed. The B-36 didn't fly for the first time until after the end of the Second World War. It hadn't been designed with nuclear weapons in mind, but its range and payload capacity made it well suited for carrying the large and heavy early generation nuclear weapons. And the B-36 quickly became a key ingredient in Strategic Air Command, or SAC, which assumed the primary strategic bombing role in a post-war reorganization of the U.S. Army Air Force. One of the weaknesses of the B-36 was its low speed. Even with the later addition of 4 supplemental turbojets to boost speed over the target, like the example you see here, the advent of Soviet jet fighters like the MiG-15 and its successors made the B-36 vulnerable to interception. Now, while the B-36 had been under development, the jet turbine engine had proceeded from R&D to operational use, and in combination with the additional aerodynamic advancements like swept wings, it opened up new possibilities for large, fast aircraft. These were first expressed in the Boeing B-57, which I talked about a couple of years ago. And this flew nearly twice as fast as the B-36, but at the expense of a significantly shorter range. The design innovations of the B-47 influenced the evolution of the Boeing B-52, which was under design at the same time. The B-52 was originally intended to be powered by turboprops, but the advent of more fuel-efficient turbojets raised the possibility of an intercontinental range bomber with high subsonic speeds. And after a request from the Air Force to redesign the aircraft to use the new turbojets, a team of Boeing engineers devised a completely new design over a long weekend in a Dayton hotel room and submitted a detailed 33-page proposal complete with a scale model on the following Monday morning. Now, the resulting aircraft had the desired high subsonic speed, didn't have quite the payload as the B-36, and not quite so much range. But the advent of smaller nuclear weapons and air-to-air refueling meant that this wasn't really a big problem. But all of these were subsonic designs. With the achievement of supersonic flight for the first time in October 1947, thinking switched to the possibilities of supersonic bombers. A first attempt at a supersonic bomber was the Convair B-58, capable of flying at Mach 2 and with a medium range similar to the B-47. And this flew for the first time in 1956 and entered service in 1960. The B-58 carried its weapon and most of the fuel in that pod you see, most of the fuel used in the outbound flight in that pod you see under the fuselage. And this was to keep the size of the aircraft down. Make a note of this, it's a sign of things to come. Most of this happened during the tenure of General Curtis LeMay, who headed Strategic Air Command from 1948 to 1957. By 1954, the transition from a piston-powered bomber force to a turbojet-powered force was already well underway. In that era of rapid technological change, LeMay now wanted a fast transition from a subsonic force to a supersonic force. The B-58 would be the replacement for the B-47. And now a replacement for the B-52 would be needed that could fly higher and faster for optimum survival. Owing to the very high fuel consumption while flying supersonically, the initial thinking concentrated on designs that could cruise at a high subsonic speed but could employ a supersonic dash over the target. And one potential solution that attracted a lot of interest was the possibility of a nuclear-powered aircraft. Now, this idea may sound utterly insane today, but the 50s were a different era. It was the atomic age when almost anything seemed possible. The idea had been discussed by physicist Enrico Fermi as far back as 1942, even before the operation of the first nuclear reactor. Nuclear reactions are capable of generating an enormous amount of heat, so the issue just seemed to be to find a way to apply this heat source to aircraft propulsion in a practical manner. It seemed eminently doable at the time. A first attempt at using atomic power in an aircraft was the Convair B-36H. Now, this was originally a regular B-36H that had been damaged in a tornado before delivery and was rebuilt as a test aircraft to evaluate the practicality of operating a 1 megawatt nuclear reactor in an aircraft. Now, note that this 16-ton reactor wasn't intended to provide any propulsion. It was just intended to generate heat and radiation that would simulate a reactor in a real nuclear aircraft engine. It was hung on a hook in one of the bomb bays, and it was lowered into a shielded pit in the ground when it wasn't being flown in the aircraft. One of the key things that needed to be evaluated was protecting the crew from radiation emitted from the reactor. And as part of this, the original cockpit area was replaced with an 11-ton lead-shielded crew compartment with 11-inch thick leaded glass windows. Now, the NB-36H made 47 test flights between September 1955 and March 1957. It demonstrated that a reactor could be operated in flight and that shielding could be arranged to keep flight crews safe. How safe it might have been in a crash is another matter. A legend has it that the aircraft was always accompanied by a transport full of paratroopers to secure the site if it ever crashed. Simultaneously, General Electric and Pratt & Whitney were working on various nuclear-powered turbojet engines. This is a General Electric experimental design. The engines on the bottom may look familiar to some of you. They're modified General Electric J47s. Instead of burning JP4 like you would normally expect, they're actually powered by the nuclear reactor at the top. This isn't just a proof, this isn't just an illustration. This was actually built and ground operated in the late 50s. So this was intended to be a technology demonstrator for larger flight-capable engines that were to follow. The next step beyond the NB-36H was supposed to be the Convair X6, which is another modified B-36. On the X6, there's a nuclear reactor in the fuselage, but in this instance, it's actually powering the 4 turbojets under the fuselage. The way that this would have worked is that the conventional engines on the wings would have gotten the aircraft in the air, and then the nuclear turbojets would have been started in flight. Now, again, you've got the same issue. You want to keep weight down. So the reactor would have carried minimal shielding, just enough to protect the crew, and they would have lowered the reactor into a pit in the ground with a lead cover when it wasn't flying in the aircraft. And at the time, it was figured that robotic equipment would be needed to service the reactor. So 2 of these aircraft were planned, but the program was ultimately canceled before construction actually began. So at the time, the concept of a nuclear-powered bomber seemed realistic. The intended objective was a bomber that could cruise at high subsonic speeds on nuclear turbojet engines and then fly at Mach 2 in the dash to and from the target. Now, at the time, the B-52 was expected to serve all the way up until 1965. You're supposed to laugh at this point. So in 1954, the Air Force issued GOR 38 to cover a B-52 replacement intended to be in service between 1965 and 1975. And there were 4 options considered. Option 1 was a design with entirely conventional propulsion, no nukes, and with the idea that this would be in service for 1963. Option 2 had nuclear turbojet cruise, and that would be boosted with conventional turbojets to provide the supersonic dash over the target. And that was intended to be in service for 1963. Option 3 was the same as option 2, but the in-service date was pushed back to 1965. Option 4, nuclear-powered cruise and nuclear-powered dash. This was more complicated, more challenging, and it was expected that this probably wouldn't be in service until 1968 to 1970. So of these choices, option 2 was preferred. In particular, nuclear cruise allowed for an aircraft with almost unlimited range at subsonic speeds. Now, despite the preference for nuclear-propelled aircraft, General LeMay insisted that a conventional power design be developed as a backup. So by 1955, 2 programs had started. WS-110A for a chemical-powered bomber and WS-125A for a nuclear-powered bomber. As for chemical-powered, I'll get to what they meant by that in a moment. The requirements for WS-110A were challenging. It needed to have true intercontinental range to avoid the necessity for overseas bases like the B-47. A combat radius of 4,000 miles was the minimum requirement, with 5,500 miles preferred if possible. And the aircraft needed to be able to make a 1,000 to 2,000 mile supersonic dash to and from the target. It needed to be a true all-weather aircraft capable of operating under any conditions with an operating altitude of 60 to 70,000 feet. Aircraft on alert needed to be capable of launching within 3 minutes of cruise boarding, and while aircraft not on alert needed to be able to launch with 30 minutes notice. It would be armed either with freefall nuclear weapons or possibly a standoff surface-to-air missile. And also, as had been the case for recent SAC bomber designs, a reconnaissance version was planned. 6 manufacturers, Boeing, Convair, Douglas, Lockheed, Martin, and North American, were invited to bid on WS-110A and WS-125A in June 1955. Lockheed and Convair were granted contracts to develop designs for the WS-125 nuclear-powered bomber and elected not to pursue the chemical-powered contract. Simultaneously, Convair, Douglas, and Martin were putting a lot of effort into ballistic missiles, and this was for designs that would ultimately emerge as the Atlas, Thor, and Titan. And they didn't have the engineering effort to spare for the chemical-powered contract. So the competition for WS-110A boiled down to Boeing and North American, and Phase 1 development contracts were awarded to both in December 1955. A lot of the systems for WS-110A and 125A were intended to be compatible to keep the development costs down for both projects. While the nuclear-powered bomber would require entirely new engines, the conventional design was intended to use engines that were already under development. So Boeing and North American were directed to investigate using a developed version of the Curtiss-Wright J-67, a developed version of the Pratt & Whitney J-75, developed version of the General Electric J-79, the Allison J-89 seen here, and the Pratt & Whitney J-91. Boeing's engineers seem to have had a field day with this project, and here is a selection of some of the designs they came up with. I note several that look like Super B-52s, and one that looks pretty similar to the subsequent Soviet Myasachev M50 Bounder bomber prototype. And then there are other designs that wouldn't look too out of place in the Star Wars universe. I'm sure that North American's engineers were equally creative in their work, but owing to the state of North American's corporate archives after several mergers, we don't have the same kind of detail available for what they came up with. Boeing and North American both submitted their proposed designs to the Air Force in mid-1955. The final Boeing design managed to combine the desired range, payload, and dash speed by employing hinged, floating outer wing panels. The aircraft would take off with these attached, and the early subsonic part of the mission would use the fuel in these wing extensions, and there would be hinges here to allow for some flexibility. When the supersonic dash to the target was about to commence, the outer wing panels would be discarded. The remaining aircraft core would then make the supersonic dash to the target, drop its weapon, and return to base. North American ended up coming up with a very similar design, also with the floating wing panels. And this is what the core of North American's design looked like after the floating wing panels had been jettisoned. And just to convey a sense of scale, those individual floating wing panels, 2 per aircraft, are each about the size and weight of a B-47. Another thing that both designs had in common was that they were both rejected by the Air Force. General LeMay remarked, "These aren't airplanes, they're 3-ship formations." One issue was that these large, heavy aircraft with the floating wingtips could not have operated from any existing runway anywhere. Additionally, there were concerns about mounting large, floating aerodynamic objects on the wingtips of large aircraft. A similar configuration you see here, tested in the early 50s with a B-29 and 2 F-84s, resulted in a fatal crash in April 1953 that killed everybody aboard all 3 aircraft. So both Boeing and North American were instructed to go back to the drawing board in September 1956 and try again. At about the same time, it was determined that a supersonic nuclear-powered bomber was going to be a lot more complicated than expected and was not realistic prospect for such an aircraft to be ready for 1965. So accordingly, WS-125A was canceled in 1956. Nuclear propulsion still offered some compelling advantages. The ability to fly at subsonic speeds for distances limited only by crew endurance would allow a force of bombers to remain on continuous airborne alert. And the example shown here is a late 50s concept for the Convair NX-2, and this was intended to fill a role as CAMAL, C-A-M-A-L. Continuous airborne alert, missile launching, and low-level penetration aircraft. Now, despite sensationalist reports in December 1958 that the Soviet Union had built and flown a nuclear-powered aircraft, the American nuclear-powered aircraft program was canceled in March 1961. And it eventually emerged that the closest the Soviets had come to a nuclear-powered aircraft was a Tupolev Tu-95 Bear with a flying non-propulsive reactor very similar to the NB-36H. Things had changed by the time of the second go-round. For one thing, there was more knowledge about the reality of high-speed flight. By this time, Mach 3 speeds had actually been reached for the first time, and technological advancements in aerodynamics and turbine engine technology meant that instead of designing a bomber to fly and work in 2 entirely different speed ranges with matching engine optimization issues, it might be possible to design an intercontinental range bomber that could fly the entire mission supersonically. Another possibility was the employment of high energy density boron-based fuels, which offered the prospect of a 10 to 15% range boost at the expense of a more complicated fuel system. And the possible employment of alternative fuels like this is why WS-110A was referred to as the chemical-powered bomber. Now, of the previous candidate engines, the Curtiss-Wright J-67 had been canceled, And the Allison J-89 was eliminated because it was optimized for subsonic flight. So this left the General Electric design at upper left, which had morphed into the J-93, and the Pratt & Whitney design at lower right, which morphed into the J-58. The Air Force issued a final request for proposals in September 1957, calling for an aircraft with a cruise speed of Mach 3 to 3.2 at 70 to 75,000 feet and a range of 6,000 to 10,000 miles. This time, the designs were somewhat more realistic. They were intended to use existing B-52 bases and facilities and employ similar maintenance crews and skills. Boeing's engineers reevaluated the designs that they'd created previously, and the resulting revised design was the Boeing 804-4 with a trapezoidal wing and 6 J-93 engines in individual nacelles. This design featured a canard that folded up vertically at subsonic speeds and then folded out into the position you see here when the aircraft went supersonic. The whole nose drooped down to provide improved visibility during takeoff and landing, but there was essentially no forward visibility with the nose up. It was designed to carry a single 10,000 or 25,000 pound bomb in the weapons bay. North American's design incorporated a phenomenon recently discovered by an NACA engineer: compression lift. This postulated that a properly designed supersonic wing could ride the aircraft's own shock wave, thereby reducing drag and improving range. The most distinctive feature of the design was the folding wingtips, these folded down at high speed, and they offered multiple benefits. It improved directional stability at high speeds so that the vertical stabilizers could be smaller. It also compensated for center of gravity changes at supersonic speeds, and it also helped to box the shock wave in under the wing. The inlets under the wing each fed 3 engines on each side, and all 6 J-93 engines were arranged side by side across the rear of the wing. North American's design also incorporated a canard. The size and details of the canard changed over time, but the final version had both variable incidence and a control surface, meaning that it could be employed for both trim and pitch control. Both designs were evaluated in October and November 1957, and North American's design was judged superior to Boeing's, and the decision was announced on December 27, 1957. While this was going on, the world situation changed dramatically. The Soviet Union demonstrated its first intercontinental ballistic missile in August 1957, and then used the same rocket to launch Sputnik in October. While this was seen as catastrophic at the time, American strategic missile development was actually well underway, with initial versions of Atlas and Thor having already flown before the end of 1957. In recognition of the changed situation, Air Research and Development Command issued a statement in early 1958 clarifying that while missiles would be a vital component of strategic arsenal going forward, bombers would still be required due to concerns about the reliability, accuracy, flexibility, and relative immobility of missiles, as well as the bomber's capability to participate in limited wars. An indication of the dynamic situation was that a requirement for low-level penetration at 500 feet would now be required for the new bomber. North American signed a contract for the development of the aircraft at the end of January 1958, and the project was officially designated B-70 in February. The planned reconnaissance version of the B-70, which had been put on hold in 1956, was formally canceled in February 1958 due to the intended availability of other systems by the 1965 timeframe. And this actually referred to what at the time was the ultra-secret Corona spy satellite program that was under development. The B-70 was officially given the name Valkyrie as a result of an Air Force competition in July 1958. In the spring of 1957, North American Aviation had been awarded the contract to develop the XF-108 Rapier long-range Mach 3 interceptor. The design was intended to share systems with the B-70, including its engines and high-altitude ejection system, and thus reduce costs for both programs. The Valkyrie's design had largely assumed its final form by early 1959, but things started to get complicated on the political front. General LeMay and the other bomber generals were entirely supportive of the program. Around 1958, LeMay's stated priorities for strategic delivery systems were the B-52, in this order, the B-52H, the B-70, then the nuclear bomber, with missiles coming dead last. Contracts had been distributed widely to make the B-70 program favorable to Congress and the Senate. As the above trade advertisements will show, it was also highly favored by its subcontractors and the aviation press. During this time, missiles were making excellent progress. The first Atlas D ICBMs were successfully field tested in September 1959. The previous uncertainties regarding missiles and their performance were being resolved, with the next generation Titan II and Minuteman missiles promising even better performance. The B-70 program had already cost $300 million by October 1959, with hundreds of millions more to be spent by June 1960, and the Air Force had programmed $460 million for fiscal 1961. Costs were driven up further by the cancellation of the F-108 program in September 1959. Development costs that had been shared between the two programs now had to be carried entirely by the B-70 program. In November 1959, President Eisenhower told General Power, Air Force Chief of Staff, that the B-70 left him cold in terms of making military sense. At this point, it was anticipated that with funding as it was at the existing level, the B-70 would not be an operational system until the late 60s. The Air Force reiterated its concerns about the inflexibility of missiles and the bomber's role as part of a diversified nuclear strategy. After a further reevaluation, the administration reduced the B-70 program to a single prototype in September 1959, with the cancellation of most major subsystems. On May 1, 1960, a U-2 overflying the Soviet Union was shot down by a Soviet S-75 Dvina surface-to-air missile. While the existence of Soviet SAMs had been known, their performance wasn't, and the incident came as a rude shock. Higher and faster, which had been the recipe for bomber effectiveness for decades, was now highly questionable. The requirement to operate at low level was ultimately the doom of the B-70 and the B-58. While both aircraft could operate at low levels, they did with performance similar to the B-52 while being significantly more complex and expensive to operate. 1960 was an election year, and the B-70 was an extremely contentious issue. Congress restored $60 million in funding to keep the program alive. In August 1960, the situation changed again. $265 million was added to the budget and full-scale development resumed. A contract was signed for the construction of an XB-70 prototype and 11 YB-70 service test aircraft to demonstrate Valkyrie's combat capability. Many of the subsystem contracts were restarted. However, this only turned out to be a brief stay of execution. John F. Kennedy won the 1960 election, and after an assessment by Robert McNamara, the incoming Secretary of Defense, it was announced that the B-70 would be reduced to a research program only, with the primary intent of exploring high-speed flying up to Mach 3 in a large aircraft potentially usable as a bomber. The plan was to build 2 XB-70 prototypes not equipped with operational systems. The third aircraft would be a YB-70 equipped with the bombing navigation system, a working weapons bay, and some other systems intended for the finished aircraft. The YB-70 would have the full 4-person crew, while the two XB-70s would only carry the 2 pilots. The reducing of the B-70 program to just the prototype meant that the J-93 engine would also not need to be fully developed. The third Convair B-58 had been converted as a J-93 testbed, but was never operated in this configuration as a full-scale development program was not required. Although the boron-based high-energy fuel program had gotten as far as flight testing in the afterburner of a modified J-79, the project was canceled in August 1959. In theory, this should have significantly impacted the range of the B-70, but the employment of a special high-density kerosene fuel, which is JP-6, which is a modification of naval JP-5, made up most of the difference. Despite the repeated cancellation by 2 different administrations, Congress and the Air Force continued to try and resuscitate the program. A last-ditch effort by the Air Force, particularly by General LeMay, who became Air Force Chief of Staff in July 1961, tried to pitch the aircraft as the RS-70 for reconnaissance strike. This version of the aircraft was supposed to fly over the Soviet Union after a nuclear exchange and have the ability to pick out targets that had been missed previously and attack them. The prototype RS-70 would be built from the planned YB-70 prototype aircraft. And the program called for 210 RS-70s to be delivered starting in 1969 at a cost of over $10 billion. And incidentally, for all the figures I'm citing, multiply by about 10 to get current dollars. In March 1962, Congress directed the administration to spend $491 million more than previously planned for production planning and long-term procurement for the RS-70, slated for a vote on March 22nd. This time, this issue and the disagreement between Congress and the administration was serious enough to be considered a potential constitutional crisis. On March 19th, President Kennedy and longtime Congressman Carl Vinson, who was chair of the House Armed Services Committee, had a meeting in the White House that ultimately led to a small change in the wording of the proposed defense bill. While both sides declared victory, the deal doomed the last possibility of a production Valkyrie. Now, while the political wrangling was underway, the first XB-70 prototype had been under construction at North American's Palmdale, California plant. The Valkyrie was planned to operate at Mach 3, and at these kind of speeds, airframe heating will generate skin temperatures above 600 degrees Fahrenheit. So the aircraft couldn't be constructed out of conventional aluminum. Something a little more exotic was going to be needed. The choice was to use a stainless steel honeycomb structure like the material you see here. The skins would be brazed to the stainless steel honeycomb material to produce a light, strong, and heat-resistant structure. A certain amount of titanium was employed, mainly in the nose, and high-temperature steel was employed in the engine bays here. And I'll explain the story of this a little further in the presentation and how it got here. Airframe heating also meant that the fuel tanks would need to be inerted with nitrogen for safety reasons. The outer 40% of the Valkyrie's wings were hinged and can be folded down either 25 or 65 degrees. Zero fold was used for takeoff, landing, and subsonic flight. 25 degrees down was used for transonic and supersonic flight, while 65 degrees down was used above Mach 2.5. The improved directional stability from the drooping wingtips allowed the vertical stabilizers to be half the size they would have been otherwise. And again, to convey a sense of scale, each of these drooping wingtips is about the size of the complete wing of a B-58. The nose featured the combination of a windshield and a nose ramp that could be raised for improved streamlining at high speeds and lowered for improved visibility while on takeoff and landing. Given the wide range of speed and altitudes that the B-70s were going to be capable of, the ejection seats were designed to be capable of fully encapsulating the pilots in the event of a loss of pressurization or the need for a supersonic ejection. The capsule had a window at the front that allowed the instruments to be read, and the design allowed for some control of the aircraft from inside the capsule. In the event of depressurization, it would have been possible to maintain control of the aircraft during the descent to an altitude where pressurization wasn't needed. If the seat needed to be used, it would be fired away from the aircraft with a rocket so that it would clear the tails. Booms would be unfolded to keep the seat from tumbling. There was a landing bag at the bottom that would cushion the landing. The seat would float if it landed in water, and seat even contained survival gear for its occupant. And the seat was tested using rocket sleds and launched in the air from B-47s and B-58s to confirm its effectiveness. Because of the need to fit the retracted landing gear around the inlets and other aircraft systems, the Valkyrie had a rather complicated landing gear and gear retraction sequence. And as I'm going to be talking later about a number of incidents with the landing gear, just going to have a brief video that actually shows how the retraction sequence worked. So here's the aircraft with its gear down. You can see the main gear is tilting up and also rotating. And now the entire gear lifts back up into the fuselage. This is just going to provide context for some of the incidents I'm going to be talking about in a few minutes.
Nose gear has up and door lock. Wheel well. And both nose gear doors are coming closed, and they're closed, and it looks clear.
Okay. On March 5th, 1964, the third YB-70 prototype was canceled, so only the two XB-70s would actually be built. The first XB-70, known as AV-1, was rolled out at the Palmdale plant on May 11th, 1964. Over the next few months, it underwent ground tests to test the engines and ground handling. Significant issues were encountered with the 4,000 pound per square inch hydraulic system. Also, the taxi tests were interesting given that the aircraft's cockpit is 65 feet in front of the nose wheel. So I think that took a little bit of getting used to. The initial test pilots for the program would be Air Force project pilot Colonel Joe Cotton on the left and North American Chief Test Pilot Alvin White on the right. The other pilots that flew the XB-70s were Lieutenant Colonels Ted Sturmstall, Lieutenant Colonel Fitz Fulton, and Major Carl Cross for the U.S. Air Force, Van Shepard for North American Aviation, and Donald Mallock for NASA. The first flight happened from Palmdale on September 21st, 1964. North American was under pressure to fly the aircraft supersonically as soon as possible. There was a $250,000 bonus if they went supersonic on the first flight. If it happened on the second flight, the bonus was $125,000. If it happened on the third flight, there was no bonus. And if it happened on the fourth or subsequent flight, there was a $125,000 penalty. The aircraft continued to have hydraulic issues. The maiden flight was postponed with the last-minute replacement of a hydraulic pump, and then was unable to go supersonic when the main gear didn't fully retract. At the time of its first flight, the XB-70 was the heaviest aircraft ever to have flown. Now, after that first flight, AV-1 landed at Edwards Air Force Base, which is where the flight test program was going to be carried out. And they had some further gear issues when they landed. The brakes that were supposed to stop the wheels from spinning after takeoff didn't release on 3 out of 4 wheels on the left side, and that resulted in blown tires, a minor fire, and damage to the beam that connects the 2 pairs of wheels. Fortunately, there was a spare beam left over from the recently canceled B-70A. On the second flight, the landing gear retracted properly, but other hydraulic issues prevented the aircraft going supersonic. Emergency gear extension was needed, and the aircraft landed on the Edwards Lake bed with no issues. AV-1 finally went supersonic on the third flight on October 12th. On the aircraft's fourth flight, the wingtips were tested for the first time to the intermediate 25-degree position. After its first 4 flights, the aircraft was returned to Palmdale for structural testing and, as you can see here, repainting. There had been some issues with peeling paint on the first few flights, and the result was an aircraft that looked like it was suffering from some kind of disease. AV-1 was flying again on February 16, 1965, and this was the first time that the wingtips were deflected the full 65 degrees. Mach 2 was exceeded on the 8th flight on March 24th. During the 12th flight on May 7, 1965, AV-1 was flying at Mach 2.6 when multiple issues started happening with the inlet system and all of the engines. The cause wasn't apparent until the aircraft slowed down and was joined by its chase plane, and they reported that 3 feet of the wing apex here had broken away. When the aircraft got back to Edwards, it was found that most of the debris had gone into the right inlet duct and shut down the 3 engines on that side. 5 out of the 6 engines needed to be sent back to General Electric for rebuilding. This was particularly significant because these weren't production engines and there was distinctly limited supply. The issue was due to inadequate bonding between the surfaces and the honeycomb layer on the aircraft's skin. On a flight to Mach 2.85 on July 1st, further peeling of the skin on the fuselage and upper wing surface was noted. AV-1 finally reached Mach 3 on October 14th at an altitude of 70,000 feet. The aircraft had been flying steadily at Mach 3.02 for 2 minutes when there was a loud bang. When chase planes caught up with AV-1, a large strip of skin was found missing from the left wing leading edge. As a result of these skin issues, this was the only flight to Mach 3 made by AV-1. The aircraft was subsequently limited to Mach 2.5. In the meantime, the Palmdale plant had been working on the construction of AV-2. This incorporated a number of improvements over AV-1. The wing incorporated a 5-degree dihedral to address directional stability issues versus the flat wing of AV-1. It featured a revised hydraulic system to address the issues that had been found with the first aircraft. It featured an automatic air inlet control system versus the previous manual system. And finally, there was much better attention to quality control on the stainless steel honeycomb skin. XB-70 AV-2 was rolled out on May 29, 1965 and made its first flight on July 17th, going supersonic the first time. One visible difference between the 2 aircraft is that the radome on AV-2 was painted black, although the radar system that it was supposed to house was never installed. The changes made to AV-2 were effective. The second Valkyrie demonstrated much better directional stability, fewer hydraulic issues, and didn't seem to suffer from the skin issues that had plagued AV-1. Accordingly, AV-2 took over the high-speed flying from AV-1. One of the contract requirements was for the aircraft to demonstrate the ability to fly at a sustained speed of Mach 3 for at least 30 minutes. The engineers had figured that this amount of time would allow for the aircraft to get as hot or as cold as it was going to get in that regime. AV-2 first reached Mach 3 on January 3rd, 1966, and no skin issues were evident. Slightly earlier, on December 20th, 1965, AV-1 demonstrated that it was possible for a pilot to encapsulate himself in the ejection capsule and still fly the aircraft, with Al White flying the aircraft from within the capsule for 10 minutes before resuming normal flight. Hydraulic issues reared their ugly head on March 7, 1966, during the 37th flight of AV-1. When trouble was indicated on both hydraulic systems, the aircraft immediately headed for Edwards and the gear was extended. However, no green indications were seen, and the chase pilots reported that there were issues with both main gears. On the right side, the bogey beam had not fully lowered, leaving the rear wheels higher than the front. The left side was even worse. The beam had not lowered at all, leaving that side of the gear oriented vertically. Neither the backup nor the emergency extension system helped. Ultimately, it was decided to land the aircraft on the Edwards Lake bed. It was hoped that the shock of landing would get all four wheels on the ground on the right side. There was nothing that could be done on the left side. All that could be hoped was that the aircraft would not ground loop or have a wingtip strike the ground. During the run-out, the aircraft rolled for 3 miles, swinging 110 degrees and half a mile to the right before stopping undamaged. This incident illustrates better than anything else the immense value of the huge dry lake bed at Edwards Air Force Base for flight testing. On March 24, 1966, the Valkyrie made its only appearance away from Palmdale and Edwards, visiting an air show at Carswell Air Force Base in Texas. AV-2 flew a flight demonstration and then was a static exhibit, returning to Edwards on March 26. This would have been a show to go to. On its 37th flight on April 30th, AV-2 showed that it wasn't immune to landing gear issues, with the nose wheel getting jammed against the nose gear door. Because it was caught partway through the sequence, it was unable to retract or extend. And as you can see, one of the tires has been sliced. The emergency lowering system, bumping the gear with touch and goes, and pulling G were tried to extend the gear to no avail. Fortunately, a full load of fuel was aboard, and so the aircraft circled round and round at Edwards while the engineers tried to come up with something. What they came up with was a process to bypass part of the door's electronics by shorting them with a paperclip. Unfortunately, neither of the crew had a paperclip with them, but Joe Cotton was able to improvise something with a clip from his oxygen hose. Very fortunately, he also had a screwdriver with him to undo the terminal cover. So Joe Cotton went back into the instrumentation bay on the aircraft and was able to trip the circuit. This worked, and the chase planes were able to see the gear extend. Now, there was still the matter of the slashed nose gear tire. White and Cotton elected to continue to circle to burn off fuel and lower the landing weight. Okay. Here's AV-2 coming in for its landing. The plan was to lower the nose wheel gently with the intent of going around again if there were control issues. And then they'd make a second attempt with the runway covered in foam. This went out the window as soon as the main gear touched down. The brakes locked and 6 out of 8 main tires blew and caught on fire. Al White is doing his best here to keep the nose wheel in the air for as long as possible. And as you watch, as the nose wheel hits the ground, that slashed tire disintegrates. Remember that dramatic landing I was talking about from that documentary? This is it. Okay. Now, despite the dramatic appearance of this accident, AV-2 was repaired quickly and was back in the air on May 16th. And the quest for the sustained Mach 3 flight resumed. And on May 19th, they finally achieved it. AV-2 flew above Mach 3 for 32 minutes at 72,000 feet, doing a huge loop over the western United States. This finally confirmed that the XB-70 was capable of long-duration Mach 3 flight, essentially for as long as the fuel lasted. It also confirmed that that revised method of manufacturing the stainless steel honeycomb skins was effective, as no skin separation issues were noted. Now, one thing though, the aircraft was still not demonstrating the range that the original design was supposed to be capable of, due to a combination of overestimating the gains from compression lift, underestimating transonic drag, overestimating the engine inlet performance, and gains in weight. The range was estimated to be about 25% lower than the original requirement. This completed the Phase 1 airworthiness tests. So with the contractual requirements now fully demonstrated, the focus of the program began to shift. NASA became more heavily involved, and the aircraft's role became more of a technology demonstrator for the planned American Supersonic Transport, or SST, program. The other aircraft in the photo here is a Convair TB-58. This was the usual chase plane for the XB-70. It couldn't keep up with the XB-70 above Mach 2, but then neither could anything else that was available as a chase plane at the time. One of the principal objectives for the NASA program was to determine how severe the sonic booms generated by the American SST would be. And the XB-70 was the only aircraft similar in size to the proposed SST that could also fly at the planned SST's Mach 2.7 cruising speed. So AV-2 was retrofitted with a wide range of sensors and recorders to this end, and they set up an extensive array of ground sensors to measure the effect of the sonic boom. One concern was that the XB-70 was actually heavier than the planned SST, and this meant that the sonic boom tests had to be done with less than a full load of fuel. Generally, sonic boom testing was done with the XB-70 at about 65,000 feet and Mach 2.7. At this point, Al White and Joe Cotton began to transition out of their test pilot flying on the XB-70, so some additional test pilots would be required for the program. These new pilots for the program were Major Carl Cross, U.S. Air Force, on the left, and Joe Walker, NASA Chief Research Pilot, on the right. Walker was particularly well known for his flights in the North American X-15, and he performed the two highest altitude flights of the X-15 program in the summer of 1963. Both pilots attended ground school for the XB-70, and both flew some flights on a TB-58 to get some current experience flying large delta wing aircraft. The plan was for these pilots to get checked out in the XB-70 and then take over the test flying from their predecessors. Carl Cross got checked out first, making his first flight in AV-2 with Al White on June 8th. In addition to being a checkout flight for Carl Cross, the June 8th flight also carried out some airspeed calibration runs and a sonic boom run. With these duties completed, AV-2 then became the center of a formation of aircraft for a photo shoot, which assembled at 8:45 local time southwest of Edwards. The other aircraft in the formation from left to right, a Northrop T-38, McDonnell F-4C Phantom, Lockheed F-104 Starfighter, and an F-5A Freedom Fighter. All the aircraft in the formation were powered by General Electric engines. The photos from the shoot were going to be used as promotional material by General Electric, possibly on the cover of their annual report. Even the photo shoot for the shoot was General Electric powered. It was an early Learjet borrowed from Frank Sinatra. The F-104 in the formation was NASA 013, piloted by Joe Walker. Joe Walker was to the immediate right of the XB-70. The formation had originally been planned to take 30 minutes, but the Learjet requested an extra 15 minutes to finish up. Finally, at 9:26, the photographers were done and the formation prepared to break up. Then, White and Cross in the XB-70 heard a thump and heard "midair, midair, midair" over the radio. The tail of the F-104 had struck the right wingtip of the XB-70. The F-104 then rolled over the top of the XB-70, severely damaging both vertical stabilizers. The F-104 disintegrated and Walker was killed instantly. The XB-70 continued to fly straight and level, and despite the thump, White and Cross were not initially aware that it was the XB-70 that had been hit. Then the aircraft started to roll, and when White attempted to correct, AV-2 went out of control, rolling rapidly. During the second rotation, the left wing tore off. Al White was able to encapsulate, although his right arm got caught in the closing door, messing up the ejection sequence. It's not known what happened to Carl Cross at this point, but he never started the encapsulation procedure. AV-2 crashed northwest of Barstow, California, killing Carl Cross. Al White's ejection capsule malfunctioned and the landing bag that was supposed to cushion his landing didn't inflate. He suffered a 44G impact when the capsule hit the ground. Despite this, he didn't break any bones and returned to flight status 3 months later. But he never flew the XB-70 again. The investigation concluded that from his position in the formation, Walker was unable to see the wing of the Valkyrie without uncomfortably looking back over his left shoulder, and that he was likely maintaining his position in the formation using the Valkyrie's forward fuselage. As a result, he was unable to perceive his position relative to the Valkyrie and drifted into the right wingtip. The photo shoot had not been authorized by the Air Force, and several officers were reprimanded for participating without seeking higher approval. Now, this is a piece of AV-2, recovered after the accident, brought by Jim Jackson, who's visiting us today, who in some ways I think would probably be a better person to do this presentation than me. But it's extraordinary. I think Jim thinks this is probably from the engine bay. It's an extraordinary artifact to hold. With AV-2 destroyed, the only possibility of continuing with the sonic boom program was with AV-1. AV-1 had been out for maintenance and modification at the time of the crash, and part of the effort involved repairing any damaged honeycomb skin that was found. When AV-1 flew again in November 1966, its former speed restriction of Mach 2.5 was raised to Mach 2.6. AV-1 carried out the remainder of the flight test program at speeds up to Mach 2.57. The sonic boom test showed that a large aircraft could generate overpressures strong enough to cause damage. And moreover, when the XB-70 made a turn, its shock waves could converge and double the overpressure on the ground. Testing with AV-1 also correlated in-flight performance with SST simulators, measured structural response to turbulence, determined handling qualities during landing, and investigated boundary layer noise, inlet performance, and structural dynamics. A final series of tests investigated high-speed buffeting as a result of clear air turbulence for an SST, with the intent of reducing passenger discomfort, reducing pilot workload, and improving aircraft structural life. The aircraft was fitted with two small vanes to generate structural vibration, which could then be damped out by the aircraft's stability augmentation system. Finally, NASA recommended that any future SST should feature a less complicated landing gear. The program wound down by the end of 1968. NASA had accomplished the majority of its goals, and the Flight Research Center was having budget issues. AV-1 was going to need major maintenance in the near future, including resealing its fuel tanks. NASA ultimately got two YF-12s from the Air Force to handle their future high-speed testing requirements. AV-1 made its final flight on February 4th, 1969, a subsonic flight from Edwards to Wright-Patterson Air Force Base. And here is AV-1 making its final landing at Patterson Field. AV-1 then went on display at the United States Air Force Museum. Now, at the time, the museum was at its original location at Patterson Field, and the XB-70 was displayed outside there from 1969 to 1971. However, there had been plans for over a decade to move the collection to a new home at Wright Field. So in 1971, the museum's exhibits, including the XB-70, were moved by road for 10 kilometers to the new location at Wright Field. Fortunately, it was small enough not to require dismantling. I think at one stage it just squeaked by with 6 inches of clearance. For many years, the aircraft was displayed outside as a gate guardian of the museum. And this is what it looked like the first time I saw it in November 1981. It moved inside when the museum's second gallery was built in 1988 and has since been moved around a couple of times. For a while in the early 2000s, it was housed in the museum's annex, where it was a very tight fit and damn near impossible to photograph. You couldn't get back far enough to get the whole thing in. Since 2016, it's been housed in the museum's R&D collection in very distinguished company. Very occasionally, it has been temporarily moved outside to allow other aircraft in the gallery to be repositioned. Okay, that's the end of my talk. Now, if any of you have been looking at the photo credits, you will notice that the name Terry Panopoulos comes up a lot. Terry was enormously helpful in making this presentation happen. He supplied me with an enormous number of images. This presentation wouldn't be half as good without the material that he supplied. And I just wanted to acknowledge his contribution because it's a major one. Some other notes on image and video sources, including Jim Jackson, who is with us today. And finally, my major source for the presentation. If you are interested in the subject of this aircraft, if you want to know more than you're going to get in an hour of listening to me yammer, get this. It's a superb book. There's an amazing amount of detail there, and you'll learn everything you could possibly want to know. The book isn't currently in print, but it's available on the used market, so I heartily recommend it. Terry was a major contributor to this book. He also told me that he's on the verge of retiring and he's thinking of writing a book of his own. I think that if he comes up with something, it'll be good, so keep an eye out for it. Okay, I'd be happy to take any questions. Are we going to be doing the microphone thing? Okay, any questions? Oh, who's got the microphone? Oh, that microphone. Okay. All right. Sorry.
I'm just curious to know if North American Aviation poached any of the Avro employees, engineers, either after the Arrow was canceled or even before.
I'm not sure. The question was if North American Aviation approached any of the Avro engineers after the Arrow cancellation or before. Truthfully, I don't know. I'm not aware of anybody. That doesn't mean there wasn't anybody, merely that I'm not aware of it. Actually, no, Jack Woodman went to work for Lockheed rather than North American.
Okay. And can you tell us anything more about how a nuclear reactor helps produce thrust? Does it produce steam which goes into the...
Well, the question was how a nuclear reactor or how a nuclear aircraft engine would work. And the idea is that it produces heat. So in the illustration, essentially the reactor is just providing the heat that normally there we go. So in the photo here, the reactor at the top there, and you can actually see that the inlet of the engine is normal, and then it goes through the compressor, and then it goes up into the reactor. It's heated, then it goes back down and runs through the turbine. So it's like a completely normal aircraft engine, except that the heat is being supplied by the nuclear reactor instead of by combusting jet fuel. Now, obviously, that's a gross oversimplification. There are things like shielding this the actual photograph of this thing in service on the ground has a huge amount of shielding around it, so you can barely even see this part. And there are also small problems like if the shielding inside the reactor is not perfect, then the exhaust will be radioactive. So there are probably a lot of reasons why nobody has revisited this. It sounds simple, but it's actually vastly more complicated, and that's probably why nobody ever got it to work, or at least nobody was willing to put in the time and expense that would have been necessary to make this practical. Okay, further questions? Anybody still awake?
I got a comment.
I'm aware that I think that originally the formation was intended to contain a B-58 because that was another General Electric powered aircraft, and then for some reason that didn't happen, so the formation was just the 5 aircraft you saw.
Yeah.
I'm aware of that. The official, again, there's actually a copy of there's a copy of the official investigation report in the book. I had to sort of compress it down a bit to fit in the presentation. But essentially their thinking was that because of the configuration of the XB-70, Walker couldn't see the wing. So he was formating on the fuselage and got confused on the distance because he couldn't see what he was closest to. If you look here, you can actually see that there are a couple of lines marked on the tail and another here. These, I think, were formation marks that they put in place subsequently so that there was something for somebody who was formating on the aircraft to be able to line up with. So I'm pretty sure these were put in place after the accident because you don't see them on photographs that were taken before. I understand that it... Possibly. I understand there was a B-58 in the vicinity. I think originally the plan was to get one in the formation, and that didn't work out. But yeah, that was in the report that that was possibly a consideration. Any further questions? Yes?
Well, you mentioned that it was the heaviest airplane that was flying.
At the time of its first flight, yes.
Do you know what the maximum takeoff weight is?
I'd have to look it up in the book. But yeah, at the time it was, I'm sure that it was beaten subsequently by the 747 and maybe even a 60 series DC-8 may have been heavier. But at the time, this was the heaviest aircraft that had ever flown. Yeah, okay, thank you.
I think the round of applause is due to Martin. I am always in awe of your research, Martin, and I think this is just another example of your tenacity in looking for information.
It's all in having the right source. This is where the credit belongs.
I'm afraid we do not have a copy of that upstairs. But on behalf of the chapter, Martin, thank you so much for doing that yet again. That's a small token of our appreciation. Appreciate that.
Okay.
And as usual, there's another task to be done.
Yes, okay.
Can I have tickets, please, for this explains book?
All right. It's, last three are 885.
Oh,
Okay.
you have a shot. We had a second item donated by Terry Ward today. A picture of the arrow with, I think it's a swim bird above. All right, Terry? So if you could pick another one,
Okay.
please.
All right. Okay, and this one, last three, 880.
Oh, okay.
All right.
All right, thank you very much. Once again, Martin Senior, thank you so much. Excellent job, always.
Glad you enjoyed it.
I hope we'll see you again this time next year.
Oh, yeah, I'm already working on a subject for next year.